Hi, we talked in the last video about functions, and we finished off the video by noticing that certain values can't be plugged into certain functions. So we're going to study that particular idea in more depth during this video here. Now first, a few definitions. If we have a function f, then we say that the domain of that function is all the allowed values of the independent variable. So it's going to be all the values that we can plug into the function. Now sometimes the domain is explicit, as in the example right here. We're told that f of x has this nice rule, it's equal to 8x minus 3, but our independent variable x can only be values greater than or equal to 7. So 9's fine, 10 pi is fine, a billion is fine, but negative 6 is not, and even negative 6.9999999 is not. Now sometimes the domain is implicit. If we look at our function g down here, there's no explicit restriction, but we notice in the denominator we've got an m plus 1. We've got a variable in our denominator, and we know that you can never divide by 0. It can't be done. It's one of the fundamental rules of arithmetic. So that means that that m plus 1 can never be 0. Can we write that in a bit of a simpler way? Yeah, a more simple way of writing it would be m can't equal 1. Negative 1. Okay. So negative 1 is the only value we could plug into our function g that would cause problems. Any other value of m that you plug in there is okay. So the domain of g would be all real numbers except negative 1. Now if you think for a moment about what we're going to be doing, we'll express that domain, and the most natural thing would be to use interval notation. But before we get to those practical examples, can you think of some things that might show up in the equation for a function that might restrict its domain? So we saw one already. If we have a denominator, we know denominators can never be 0. Now it doesn't mean that your variable can't be 0, it means the whole denominator. In the previous example we saw m couldn't equal negative 1. Now this also gives us a little recipe on how we can figure out what the domain should be. We can find all the values that make the denominator 0 and throw them out of the domain. Now how can we find those values? Essentially we're solving an equation like we did just above, right there. Now there is another operator or object we might see in the definition of a function that would restrict the domain. The other thing you might see, and we saw that in the previous video, was if you've got a square root. And in fact, any even root, a fourth root, a 10th root, they all have this same property that you can't take an even root of a negative number. Or put another way, you can only take an even root of a non-negative number. Now, just writing that down, it gives us a recipe on how we can find the domain. All we need to do is take everything under the even root sign, we actually have a name for that, it's called the discriminant, and make it greater than or equal to 0. That's an inequality. And we talked in the first class about, or the first video, about how to solve inequalities. So we'll take the expression under the even root sign, and set it to be greater than or equal to 0. And we'll solve that inequality. So let's try a few examples here, just to see for particular functions what their domain would be, and we'll be on the lookout for denominators and even roots. By the way, there are a few other things that will restrict the domain, but we'll talk about them later in the course. Now if we look at our first function here, we've got x squared plus 2 as our expression, and there's no even root there, there's no denominator. So our domain is going to be all real numbers. Now to express all real numbers in interval notation, I'll say it's the open interval from negative infinity to positive infinity. And in this exercise, we're also going to draw our interval on the real number line. Okay, so this one's very easy to draw. It is the real number line. Another way to think about this first question is that what we're being asked to do with our function is take the input, square it, and add 2. But every real number can be squared, and all those results can have plus 2 added to them. We're never going to run into any problems. Okay, so any real number is fair game as an input to that function. For the second example, we see that we've got a denominator, and we know that denominators can never be 0. Now our denominator is r plus 2, so it can never be 0. There's the algebraic way of writing that down. But of course we don't want to stop there. Let's say something about r itself, make it as simple as we can. And we learn that r can't be negative 2. So any real number is fine except negative 2. So that means that our domain, well, maybe let's draw the picture for this one first. There's our real number line. We know that negative 2 is important, and we know that it's excluded from the domain, but everything else is included. So that would be our picture. So that means that our domain is going to be all real numbers from negative infinity to negative 2, excluded, and then we'll pick up again excluding negative 2 to infinity. Okay. For our next example, number 3, we notice we've got a square root. It's an even root, so we'll take what's under the square root sign, the whole thing, and we'll make it greater than or equal to 0. So we'll solve that nice linear inequality. Don't forget to change the direction of the inequality sign if you divide or multiply by a negative number. And we find that s has to be less than or equal to 3. So this time when I draw my real number line, my interesting value is 3. Now 3 is included in the domain, and everything less than or equal to 3, everything to the left. So my domain will be from negative infinity to 3, including that 3. Now for question number 4 here, looks pretty tricky. Okay, we have two different things going on at once. Each one of them is going to give us a restriction, and we need all the restrictions to be obeyed. If we look at our second term, we have a denominator that's simply t, and that tells us that t can't be 0. But in the first term, we have a square root, and under it is t, which tells us that t has to be greater than or equal to 0. So we need both of those things to happen at the same time. So, overall, what have we got? We know that 0 is where everything's happening. For the first part, we see that t has to be greater than or equal to 0, but in the second part, we see it can't be 0. So the way to express that would be by saying that t has to be strictly greater than 0. So then our domain is going to be from 0 to infinity. Now for our last example here, we have an explicit restriction, so we'll keep a very close eye on this. This has to happen. Our input values, q has to be greater than 1. So automatically, and there's no particular reason for this, we're just told it in the question, q must be greater than 1. However, we also notice that our equation, or our expression, has a denominator. And we see that that denominator contains a variable, so we're interested in when that denominator would be 0. Okay, so if we solve that little equation, or non-equation, I guess, since it's not equal to, we find that q can't be 2 either. So we have that q must be greater than 1 and q cannot be equal to 2. Let's draw a picture. So here 1 and 2 are both important values, and both of them are excluded from the domain. However, any other value bigger than 1 is in the domain. So that would be a picture of my domain on the real number line. So let's write down that domain with interval notation. So we're going to exclude 1 and go up to 2 and exclude it, along with, we'll start again, excluding 2 all the way to infinity. So we've seen several examples here, some with denominators, some with square roots, and some with explicit restrictions. And we've studied how to find their domain. Now I'd like to talk about another idea, the idea of range. And this is often a lot trickier to figure out. There aren't any hard and fast rules. In fact, what we need to do is start with our input, the independent variable, look and see what the function does to that input, and see if we can't logically deduce some restrictions on the output. Okay, so this is a little bit trickier. Now, if I look at my function here, g of z is equal to z squared plus 6. Now, from our domain, we know that z can be any real number. You can square any real number you like and add 6 to it. But if you think about what squaring does, if you take any real number z, z squared automatically is greater than or equal to 0. When you square a real number, the result is always non-negative. So then, if I add 6 to that, I always end up with a number greater than or equal to 6. Okay? So that tells me that the range of this function is going to be all real numbers greater than or equal to 6. No matter what z you plug into that, your final calculated value will always be at least 6. So if you look back at what we did here, our work, what we tried to do is start with the input and build up, using order of operations, exactly the same expression that shows up as our function. Okay? So we try to take our independent variable and say something about this is really the dependent variable, or the value of the dependent variable, z squared plus 6. Now 3q plus 4, this one is a little bit strange, although if you think about its graph, and we'll talk about those in the next video, it does make a fair bit of sense. Now again, q can be any real number. Okay, we don't have any denominators, we don't have any even roots. If you triple a real number, I really can't say anything about it. You're going to get some other real number. We don't know that it's going to be positive or greater than or equal to 7 or an integer or anything about it. Okay? And if you add 4, we still don't know anything at all. Okay? So our range in this case is a little bit strange. It can be any real number. Okay, so when we tried to build up our function itself, we never got any restrictions at all. So our range can be all real numbers. For our last one, we know the domain is t must be greater than or equal to 0. It's all the real numbers, 0 included, up to positive infinity. Now, if you square root a non-negative real number, your output is always going to be greater than or equal to 0. If you try in your calculator to take the square root of any number that you're allowed to, you will always get a non-negative answer. So then if you subtract 5 off of that answer, you'll always get an answer that's greater than or equal to negative 5. So our range for this final function will be all the real numbers from negative 5 up to infinity. Okay? Again, finding range can be a bit tricky. You kind of have to make it up as you go along. What you're trying to do is take your domain or your inputs and slowly build up the expression that we see for our function using order of operations. And any restrictions that come about as a result of that, they will affect our range. Thank you.